Hello everyone, this is Kirti along with my friend Varsha. Today we are here to make you know something about a very important topic, that is deadlocks in operating systems. Firstly, as we all know that every process in a system will be executed by using the CPU resources. These resources will be allocated to the processes by the operating system of the computer. The process in operating system uses resources in the following ways, such as it requests a resource, uses the resource, and releases the resource after its completion. Coming to a deadlock situation, it is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some process. We can say that a deadlock is a very big problem in computer's operating system, because if there exists a deadlock, the performance of the computer will be degraded and the processes which we are submitted for execution will never complete their work. Let us see a real life example for deadlock. Consider there are two trains, train 1 and train 2. Both are traveling in opposite directions, but there is only one track and both should travel on the same track. Here, only one can execute if other gives the way. Otherwise, both cannot perform their work and they cannot be in their way. Here, we can say that there exists a deadlock because there needs to be an adjustment, or one should sacrifice or move side away or left by to complete the other process. Coming to the example in operating systems, we can say that um, it is somewhat similar to the trains example. Let us consider there are two processes, process 1 and process 2, and also resource 1 and resource 2. Here, the process 1 is allocated by the resource 1 and process 2 is allocated by the resources 2. Here, for completion of the process 1, it requires resource 2, and for completion of process 2, it requires resource 1. Process 1 is waiting for the resource 2 and process 2 is waiting for resource 1. For completion, they are both dependent on each other. Here, if process 2 releases the resource 2, then only the process 1 can complete its work. But for completion of process 2, it requires resource 1, which should be released by resource 1. If they both release those resources only, they can complete their work. But here it is not possible. Such a situation is known as deadlock. Now, the scenario describes a deadlock in a system with two processes P0 and P1 and two tape drives P1 and P2 and semaphores A and B. Process P0 executes wait A and preempts, meaning it is waiting for semaphore A to be available. Process P1 executes wait B, indicating it is waiting for semaphore B to be available. P0 preempts P1 and now both processes are in a waiting state. P0 waiting for A and P1 waiting for B. This creates a deadlock because neither process can proceed since they are both waiting for a semaphore held by the other. Let us assume that the space the space is available for allocation of 200 kilobytes, and the following sequence of events occurs. In the given scenario, two processes P0 and P1 are requesting memory allocation in a system with the total space available for allocation of 200 KB. The sequence of events is as follows. Process P0 requests and presumably receives 80 KB of memory. Process P2 requests and receives 70 KB of memory. Process P0 again requests a 60 KB of memory and process P1 requests additional 80 KB of memory. Now, the statement mentions that a deadlock in this context means that neither process can proceed because each is waiting for the other to release the resources it needs to continue. In this case, if both P0 and P1 progress to their second request, there will be holding onto memory that the other process needs to proceed. P0 is waiting for 80 KB more, which P1 holds, and P1 is waiting for 70 KB more, which P0 holds. This results in a circular wait situation where neither process can release the resources and other needs, leading to a deadlock.
Now, let us learn the topic deadlock characterization. We can describe a deadlock with the help of these four conditions as well as a resource allocation graph. In this video, we are describing a deadlock with the help of these four conditions. These are necessary conditions for deadlock to occur. The first condition is mutual exclusion. The second one is hold and wait. And third one is no preemption. Fourth one is circular wait. If these four conditions occur simultaneously in the system, then deadlock may occur in the system. Here, we can't give 100% guarantee about deadlock occurrence. If these four conditions occur simultaneously, there is a possibility for deadlock occurrence. Here I think you understand that we can't say for 100% that deadlock will occur if these conditions are there, but there will be a possibility for that occurrence. And now let us look at first condition, that is mutual exclusion. Mutual exclusion means a process can use only one resource at a time. That means the resources are non-shareable by default. By default, it is not possible to share any resource by multiple processes. If a single resource is shared by multiple processes then at the same time, then the results won't be accurate. There may be some wrong results. Let us check that we shared a printer between two processes simultaneously. Then we will get a printing as combination of those two processes. Let us take processes as P1 and P2 and printer is shared between P1 and P2, then combination of process P1 and process P2 will be the output of the process, which means that we got wrong results. So if multiple exclusion occurs, then there is possibility that deadlock may occur. If we eliminate multiple exclusion, we can avoid deadlock in system. There are chances of deadlock because of mutual exclusion. Then now let's go to next one, hold and wait. Hold and wait means process holds some resource and is waiting for some other resources, but those resources are required by some other process. Here, a process can hold multiple resources and still request more resources from other processes which are holding them. In the diagram here, process 2 holds resource 1, resource 2 and resource 3. and is requesting resource 1, which is held by the process 1. Here, for this system to work for the system to work smoothly, process 2 should um, get resource 1, but here resource 1 is not completely executed by the process 1. So this will lead to deadlock situation. If there is no hold and wait, then there will be no deadlock in the system. Next one, no preemption. Already we know about preemptive CPU scheduling algorithm and non-preemptive CPU scheduling algorithms. Preemptive scheduling algorithm means during execution, CPU can print process. That means CPU can stop execution of a process, but in the case of non-preemptive algorithms, the CPU cannot stop execution of the process. Here it means that in preemptive CPU scheduling algorithms, we can stop one process and continue with the another process. But in the case of non-preemptive CPU scheduling algorithm, that is not the case. There we have to complete the execution of one process. Only then we can get to another process. That is what about preemptive and non-preemptive scheduling algorithms. Here we can see no preemption. It means a process cannot release resources until it completes its execution. A process can release its resource only after it completes its execution. So here, based on the given diagram, process 2 cannot preempt resource 1 from process 1. It will be only released when process 1 relinquishes it voluntarily after its execution is complete. Here, preempting means acquiring it. Like preemption means if process 2 wants the resources from resource 1, it can get it, but here it can get it by stopping its process, but it's not possible in this case. No preemption will be a condition of deadlock, and these will lead to deadlock situation. Next one is circular wait. A set of processes are said to be in deadlock state if one process is waiting for the resource which is allocated to some other process. Here, a process is waiting for that means a process is waiting for the resource held by the second process, which is waiting for the resource held by the third process, and so on till the last process is waiting for a resource held by the first process. For example, process 1 is allocated resource 2 and it is requesting resource 1. Similarly, process 2 is allocated request 1 and it is requesting resource 2. This forms a circular wait loop. Here in this diagram we can see that process 1 requests for resource 1, but request 1 is allocated to process 2. In the same way, process 2 requests for resource 2, but it is allocated to the process 1. Here all processes are dependent on each other. Only after execution of one resource which is using the means, here resource 1 is used by the process 2. So process 1 need to wait for its complete execution by the process 2. Only then will it get the chance to get the resource 1. And in the same way, resource 2 is allocated to the process 1. Only after successful execution of the resource 2 by process 1 will process 2 get the chance to uh, take resource 2. This also causes the deadlock situation where deadlock occurs, and these four conditions leads to deadlock. which means that if these four conditions satisfy, there may be a possibility of deadlock, but we can't say for sure about it. And I think you understand the topic well. Okay, and thank you.